Okay, guys, let's get it started. So today, this is, let me think here. This is kind of like the last nuts and bolts lecture for open channel flow. And so the last real topic that we'll talk about, where we talk about equations and stuff like that. And then we'll get into actually how we model this. And so we can do calculations on paper, we'll do a spreadsheet calculation with this, but really what we use all this for is in actual models. So a hydraulic model, open channel flow model called HEC-RAS, HEC-RAS. And that model we'll talk about on Thursday, and we'll have you guys do just kind of a tutorial run through exercise to become familiar with it. But today's topic, gradually varied flow, is actually what drives, it's the equation or the theory behind what drives those models. And so our learning objectives today are to compare energy losses and the associated water surface profiles among uniform flow, rapidly varied flow, and gradually varied flow, which we call GVF, gradually varied flow. So we'll compare, we started with uniform flow, then we talked about rapidly varied flow, and then now we're going to talk about, which is like hydraulic jumps or, going from critical, like choking, like looking at flow over short distances where we have minimal energy losses and seeing what happens when you do a step or change the width or something like that. All right, so once we compare them, we're going to categorize different gradually varied flow profiles. Do you guys like my bracelet, by the way? Just noticed that, got it this morning. So there's different kinds of gradually varied flow profiles, and they're a function of slope, typically, in relation to the discharge. So you can have steep or mild or critical slopes. And then whatever the slope is, that will influence what the gradually varied flow water surface profile, so water profile or water surface profile looks like. So do we go from normal depth to critical depth? Do we go from normal depth to critical depth to a hydraulic jump? What does the transition look like from one point to another? And then finally, we'll derive the equations for the standing step method, which is the method we use to calculate the water surface profile for a rectangular channel. And so this is the smooth transition from one kind of depth to another as the slopes changes, as the channel changes. We'll do this for an actual prismatic channel. This is like the easiest thing, and then we have numerical models like HEC-RAS, HEC-RAS. It's called River Analysis System, and that's what we use to actually model this. First, let's go over the quiz, though, to do that. Okay, so question one was gradually varied flow is different from uniform flow because, and I'll have you guys say yes or no as we go through. The channel in which GVF flow or gradually varied flow occurs may have different widths, cross sections, or slopes as you move downstream. Yes or no? Yes. Okay, so we'll check that one. The normal depth may not be achieved. Is that true? Gradually varied flow channel. Yeah, that's the whole point, is normal depth, you really only achieve that in kind of theory or a channel that is like long and straight for kilometers or miles. So you're always transitioning from one kind of flow regime to another, and you're always approaching normal depth, but you're rarely ever achieving it. The surface water slope may not be equal to the bed slope. Is that true for gradually varied flow? That's also true. And that was the big difference between uniform flow. Is uniform flow, everything's parallel, or everything's kind of working together and in balance. But in gradually varied flow, we're just transitioning. We're always in transition. And then finally, the channel in which gradually varied flow occurring is prismatic with a constant slope. No. All right, that's a uniform slope or uniform flow channel. Great. True or false? Gradually varied flow, the water surface profile, also known as the hydraulic grade line, is parallel to the bed profile. Is that true? No. That's basically a restatement of the last part of the previous question. Under gradually varied flow, we can use a uniform flow formula to calculate the energy loss between 2 points that are relatively close. And hence we can calculate the water surface profile between those 2 points. This is a little bit trickier, but yes. So we actually, and we'll do that for the last part of this, we use the Manning's equation to calculate the friction losses between 2 points. And we can use those friction losses then to say what would the change in water surface elevation be between those 2 points. So we actually can get a kind of a curvy type of profile. Okay, then finally we need to match these things, and this is where we get into slopes. Is a slope mild or steep? Depends on the discharge, it depends on the normal depth relative to the critical depth, and that's how ultimately we determine this. So a mild slope, our normal depth is going to be greater than the critical depth. This means our normal depth is subcritical, which is a little counterintuitive because subcritical, remember, is slow and deep, and it's greater than critical depth. So whenever we have a mild slope, the flow is always going to be trying to come up, up, up towards normal depth above critical depth. For a steep slope, it's the opposite. If we use Manning's equation to calculate the normal depth, it's actually going to be supercritical. So the Froude number, what would the Froude number be at our supercritical flow?
The Froude number, I'm not sure.
That's okay. So the Froude number equals to what at critical flow? Do you remember what it equals to? It equals 1. So it's the Froude number equals 1, and it basically tells us if we have subcritical flow, which is deep and slow, or supercritical flow. And if we remember, the Froude number is the ratio. I should put it. Froude number is equal to velocity over the square root of dg. Let me just double check that because I need to know this, but I always forget the Froude number. Froude number. Yes. Give you guys good information. Okay. We can write this as y. So y is depth. Actually, sorry, you can't see that. How about this? We're gonna share the whole screen. I'm gonna bring this over. And we'll do that. And we'll do that. Share screen. There we go. Okay. So this is our Froude number. This is y right here. And the idea is we have the velocity of the flow, and then we have the square root of yg, so depth and gravity. And this is actually called celerity, which is wave speed. And if we were to throw a pebble in a stream, it's going to make a wave. And if that wave speed is going to be relative to yg, that wave speed is, if it's faster than the flow, then it can go upstream and downstream. But if the flow velocity is faster than the square root of yg, the speed of the wave, then those waves that the pebble makes get washed downstream. That means we have supercritical flow. So when Froude number, when Froude number is greater than 1, we have supercritical. And that means the velocity of the water is faster than that wave speed. It has those special properties. It also means, should be writing in my folder, Froude number is greater than 1. If this is our specific energy curve, which for a given energy, where is my flow depth going to be under supercritical? Is it going to be on the top or bottom? The bottom, okay. So this is my y supercritical. And this is my y subcritical. Remember, we can have two different complementary flow depths at a given specific energy. And this is Froude number greater than 1, and this is Froude number less than 1. And Froude number is equal to V over square root of gy. Okay, so that's a quick thing. When we calculate normal depth, y normal, using Manning's equation, right? When we calculate normal depth, our y normal for subcritical flow is going to be greater than our critical depth. And then for supercritical, our y normal is going to be less than critical depth. And that's just the way these things work. So we'll look at how that actually plays into what a mild slope, steep slope is. But for a steep slope, the slope is steep enough that it makes that water go fast and shallow, right? So here's our steep slope. Here's our flow. And so if we were to calculate our critical depth for this really steep slope, it's going to be somewhere up here. But our normal depth is actually going to be below that. So we'll look at some examples of that. And finally, for critical slope, you can actually design a channel to create critical flow in it for a given discharge. So the normal depth would be equal to the critical depth. How'd we do? Oh, didn't put that answer in. Okay. Any questions about that before we get into gradually varied flow in more detail? All right, so we talked about our learning objectives. Let's look now at revisit our definitions here. So for uniform flow, we remember that the depth doesn't change downstream. We're in perfect balance. If there's friction that's pushing against the water, the flow acting along the wetted perimeter, and then we have gravity, potential energy being converted to kinetic energy. And those things are in balance because we have a prismatic channel. So it looks, you could slice it in half and it's going to be equal on either side, either a rectangle or a trapezoid or a triangle or a circle. And everything's in balance. And so the water surface slope is parallel to the bed slope. And this ratio here, so the change in depth in the downstream direction, so dy would be the change in depth as we move downstream in the x direction, that's equal to 0. So there's no difference, there's no slope in the water surface profile relative to the bed. And our energy loss from friction, head loss, is going to be equal to the change in elevation. Another way to say this is that our head loss over length, so if we take the Manning's equation and calculate the head loss over length, so this is the slope, the energy slope, SE, is equal to our bed slope, dz over dx. So SE is our energy slope, and S naught is our bed slope. That's uniform flow. And often, because it's easy to calculate uniform flow and you don't need a computer program to do it, you can just do it, on a spreadsheet or in a calculator. We often make the assumption that flow is uniform. And that assumption we need to check sometimes. Because if it's not uniform, could it be a gradually varied flow situation? Often it is. And how is that going to change your design? So this is one of these key things. Uniform flow pops up all over the place when it comes to open channel flow design and calculations. However, it's rarely ever achieved, so it's an approximation. And with any approximation, we need to check that it's valid and that the assumptions that go into it are valid and that it's not going to make us do a faulty design or an invalid design. So for rapidly varied flow, there's two different situations. One is we talked about the choke problem, and you guys have that problem in a homework due this week. for rapidly varied flow, we can either assume that the change in distance, the delta x, is so small that energy losses are negligible due to friction. And so we can calculate problems like choke, or how does a water slope or water depth change when you narrow the channel or do a jump or something like that. So we can use these kind of simplistic assumptions to then calculate how depths are going to change. So that was the choke problem for rapidly varied flow. But then we also have the hydraulic jump, and I posted a video on that, might have been a week and a half ago now. And so for hydraulic jump, we have a big energy loss from all that turbulence. That's rapidly varied flow. And then we go to conservation of momentum to actually calculate the sequent depth, or the depth downstream of the hydraulic jump. Now we're in gradually varied flow. And so we've already talked about this, but the depth changes slowly downstream as you go from either one slope to another slope or one width to another width. Energy loss is small from one location to the next. So we kind of break it up in these little chunks, and we assume that there's negligible energy loss. So we can use energy conservation to calculate the change in water depth from one point to another. And in this case, whereas in uniform flow, we have the friction slope. And if you remember the friction slope, for uniform flow, we calculate it using Manning's equation. So V is equal to 1, or K over N, hydraulic radius to the 2/3, friction slope to the 1/2. Often we plug in the bed slope for that friction slope, but really this is the friction slope, and you can solve for the friction slope or the energy slope as a function of velocity and Manning's roughness and hydraulic radius. So you can just solve this to actually get the energy loss in the channel due to friction. Okay, well, we assume that these two are equal for uniform flow, but for gradually varied flow, they're not. We're saying that over time we don't have uniform flow conditions, therefore these two cannot be equal. So let's just look at some examples of this. So here's some mild slope examples. And for a mild slope, remember that here's our critical depth. If for a rectangular channel, we could calculate critical depth using just the basic energy equations, specific energy equations that we derived, I think before the exam, so a week and a half ago. You can calculate critical depth. You can calculate normal depth using the Manning's equation. And so for mild slope, the normal depth is bigger than the critical depth. And in this case, this is just like a drop off or a waterfall or something like that. And because there's a big drop off, or maybe it goes to a steeper slope, we're going to fall through critical depth at some point. So this is going to be a boundary condition. And we know that at some point over this, we'll just call it a waterfall, you're going to hit critical depth, pretty much right up at the edge of it, or maybe a little bit before it, because it's going to accelerate and go into supercritical flow. So we start at critical depth, and the way these calculations work is you give it a delta y, and for a given change, say 0.1 feet or something like that, the gradually varied flow equation will give you how far back you have to go, what the delta x is, to achieve that delta y. And so it's this curved profile that is slowly, gradually approaching normal depth at some distant location upstream, maybe kilometers upstream. So if we have a waterfall in a canal and it achieves critical depth, then it's going to have this very curved profile, really imperceivable or imperceptible, whatever the word is, if you were to look at a real channel. But we can squish everything in an Excel spreadsheet and see that curve. And eventually, maybe several thousand feet or kilometer upstream, for a constant slope, will eventually approach asymptotically the normal depth. So this is an approach to critical depth. We also have an approach to backwater. So if this is a channel going into a reservoir, here we have a depth that's just controlled by whatever the elevation of the reservoir is. So the reservoir has some elevation, and our normal depth is going to approach that, and then eventually, kind of very gradually become a backwater. And backwater just means the water is backed up because of the reservoir. So that's another transition from mild to some boundary condition that's set by the elevation of the reservoir. Now let's look at a steep slope example. So here we have a steep slope. We have our critical depth and our normal depth. So our normal depth is supercritical in this case because it's steep. And the way to tell that, do I have a steep slope or not? Well, okay, it depends on the discharge. So you could have a certain discharge that would make this slope not steep. It just depends on what the critical depth is and the normal depth. And those come from the calculations that we did previously. So the normal depth, again, is Manning's equation. The critical depth is from the specific energy equation, where we took the derivative of it and found that minimum energy. So if our normal depth is less than our critical depth, we know we have a steep slope for a given discharge. And on a steep slope, that normal depth is going to want to approach that critical depth, just like we did for the mild case. We're approaching the critical depth, but we're going down because critical depth was a lower depth over that waterfall. Here, we're going up to that critical depth. And eventually we'll achieve that critical depth, which is not really stable because of the specific energy curve. It's really hard to kind of maintain critical depth. So something's probably going to change. Maybe we will have a hydraulic jump if we have a more mild slope downstream. And that's what this looks like. So we go mild, steep, mild. So under the mild conditions, the normal depth is greater than the critical depth. And as we flow, we get to a steep slope. This could be a waterfall. In this case, it's just a steeper slope. So at some point, because of that increase in slope, we pass through critical depth and then go down into our supercritical flow. So here our normal depth is less than our critical depth. Now that we're in supercritical flow down this steep slope, what's going to happen? Oh gosh, well, either we're going to keep accelerating or something's going to change. And so in this case, we have a change in slope again downstream. It becomes mild again. And in which case, the only way for this to kind of get out of, the only way to go from supercritical to subcritical is a hydraulic jump. So it's not going to smoothly transition. I'm sure there's a way to do that in like a really controlled, smooth channel, but it might not be possible. I actually don't know the answers to that. But we go from supercritical to pass back up through critical, and then we have a hydraulic jump. And all that energy that we got from the supercritical flow is dissipated, and we go back to some normal depth that is subcritical. So there's a lot of different ways this could happen. This is just an example from mild to steep to mild. And if we could all be together in the classroom and look at the flume, we could actually make this happen. But maybe I'll look up some YouTubes to show what that actually looks like. Okay, so I'm going to just tell you that there is a way to derive this gradually varied flow equation, and I'll just walk you through the beginning and then kind of jump to the end. And I'll post this if you want to go back and look at it. It's also in the book. But the way we start this problem is with the energy equation. And we say that our total energy, H, so big H would be just the total energy in the system, not specific energy. That would be E. So this is Z, Y, V squared over 2G. Remember, this is E is just Y and V squared over 2G. That's just our specific energy. But now we're bringing in our potential energy here. We can rewrite the kinetic energy in terms of Q. So we just put in A times V, and that's just an A squared to get Q squared. We have A squared on the bottom. So it's the same total head. And what we're interested in is now we're saying that the total head changes in the downstream direction. So we can use dH over dx to solve for how that water surface profile changes from one point to the other. So we'll take the derivative of H with respect to X in the downstream direction. And then ultimately we can back calculate the water surface slope, so dy, so change in depth in the downstream direction. This is our water surface profile. So this is what that looks like. We're going to do the derivative of h up here with respect to x, and this is what those terms look like. You know, dA with respect to x, dy with respect to x, dz with respect to x. And we'll note that this is our S naught right here. So we can plug that in. This is what we want to calculate, so we're going to solve for this. And we can calculate that energy loss using Manning's equation. All right, so I'm going to jump ahead. And we'll note that Manning's equation comes into the play because we need to calculate this energy loss slope. And what we end up with is this equation. So this is what our gradually varied flow equation is. And it says dy over dx, the change in water surface depth downstream as we approach a waterfall, as we approach a reservoir, as we approach some transition. So we want to know how that water depth changes in the x direction. So that's going to be equal to this derivative that we took, but then we plugged in a bunch of stuff. And we solved it in terms of the normal depth, the depth at a given location, and the critical depth. So for rectangular channel, this is pretty straightforward to actually calculate. It's a clunky equation. And this is to the 10/3 right here, by the way. That's to the third. So for, and we'll go through an example in the spreadsheet. But we have the critical depth, and we have the normal depth, and we have the bed slope in here. So when dy over dx is equal to 0, our y is equal to yn. And so if we plug in yn here and yn, we actually end up with, this is equal to 1. So 1 minus 1 is going to be 0. So when our depth is equal to the normal depth, then we get 0 for the change in water surface elevation in the downstream. When dy over dx is less than 0, so when it's negative, that means our depth is decreasing downstream. And that's when the normal depth is smaller than the critical depth. And then when our dy over dx is greater than 0, our depth is increasing.
Hey, Joel.
Yeah.
Is that a yn over y? Is that to the 2/3 or 1/3?
This is 10/3.
Oh, 10/3. Okay.
Yeah.
All
Sorry,
right.
not amazing.
No,
It's
you're
easier
good.
when I write on the board. And I'll just show you where that equation is in your book, if you want to go back and look at it. This is equation 6.25a. And the key here is this is for a rectangular channel. But for non-rectangular channels, these exponents get a little funky. And we won't actually do that by hand. That's when we go to HEC-RAS, the model, to do it. Okay. So the last point I'll make about this equation, and then we'll just kind of look at some examples, is that the critical depth is critical for classifying our flow profiles, our gradually varied flow profiles. Because y is approaching critical depth. We're always kind of in the downstream direction, approaching critical depth. But you'll also note that if you were to plug in YC here, because this is YC up here in this part of the fraction. If you put YC in here, then you get 1 minus 1 equals 0 in the denominator. And what happens when you put 0 in a denominator? Everything blows up. You get infinity. So, but that actually makes sense, because if we just draw it this way, so here's our waterfall. And as our flow approaches critical depth, our dy over dx, that starts to approach, it starts to approach infinity, because you end up getting basically dy is going to be really big and dx is going to be really tiny, right? So for a vertical line, that slope is infinite. So you end up getting a vertical line because of this drop off. So this equation is actually valid. You just approach infinity, and so you basically say, okay, at some point I'm at critical depth. This equation blows up if it actually is critical depth. All right, so let's look at some different categories of flow profiles. These are really hard to remember. And I'm not going to actually expect you to remember what an M1 is, but just know that for a mild slope, there's basically 3 different kinds of water surface profiles or transitions that we could have. And it depends on where you start. So for mild slopes, remember, our normal depth is greater than the critical depth. And the other thing to remember is that you have a downstream control. And what that means is whatever the depth is downstream influences upstream. So if I have critical depth downstream, then my flow upstream is going to be gradually approaching that critical depth. But if I change the downstream boundary conditions, if all of a sudden the reservoir fills up, then now that water surface profile is going to change. And so whatever is happening downstream influences upstream for mild slopes. And again, if you go back to that fruit number where I threw the pebble in the water, my fruit number is less than 1. That means the celerity of the gravity wave made from that pebble in the water can propagate upstream. So downstream can influence upstream. That's a key thing here. And when we do hydraulic modeling in HEC-RAS, you need to give it a boundary condition. And that's actually on the quiz for Wednesday, is the boundary condition in a model when you have subcritical flow is going to be downstream. You have to tell the model where to start downstream. So is it going to be critical depth? Is it going to be normal depth? Or is it going to be some backwater elevation? So these 3 different profiles, again, depend on what's happening downstream. Do we have a waterfall or a weir or a dam or something like that? If so, then we're going to have critical depth as our downstream control. If we are coming into a mild slope under supercritical flow, well, that flow is going to come up and eventually approach the critical depth, and then we'll get a hydraulic jump once you do that. If we're going from mild flow into a reservoir, then whatever elevation that reservoir is going to influence the profile upstream. So that's an M1, M2 is approaching critical depth, and an M3 is going from supercritical to critical. And that's what these are showing you. So Y just tells you here, Y is our flow depth at some upstream location. So for M1, Y, let's see here, M3, Y, yeah. So for M3, our Y is below critical depth. So we know we're supercritical. And that's just coming into the situation. But given the slope, our normal depth is subcritical. So we're going to eventually get up to a normal depth. For M2, we're going down over the waterfall. And so our critical depth, our Y is greater than critical depth, and our YN is greater than that. So it's somewhere in between our normal depth we could say it's equal to our normal depth or less than, and it's going to go down to our critical depth. And then for M1, which is our backwater profile, our Y becomes greater than the normal depth because of that backwater situation. Okay, for our steep slope, we have those 3 classifications still. And they're pretty analogous. So let's see if I can trace this. We'll start with the bottom one. So the steep 3, we come in like super, super critical. So we're going so fast that we're below the normal depth. And you can imagine there's this kind of like gate that you can put in a canal that makes the water come out really fast because there's all this kind of pressure coming out from that stream. So the water is going to eventually approach some supercritical normal depth. And that's what S3 is, because our normal depth is less than our critical depth. S2 tells us that maybe we came in as subcritical flow and we're going to pass through critical flow and then eventually approach our normal depth. So we came in subcritical, and then because we entered a steep slope, we're going to approach supercritical flow. And then for our S1, this is the backwater profile as before. We're supercritical, and then we're going to have some sort of hydraulic jump as we pass through critical flow, and then we'll go into the backwater of the reservoir. So your book has this figure here on page 223. And it shows what we just went through for mild and steep. And then it shows kind of different transitions for mild, under mild situations or for steep situations. Now, horizontal slopes and adverse slopes are really funky, and you can kind of, I don't know, we're not going to really deal with those. So adverse just means that the slope is kind of uphill in the downstream direction, which is weird, but I'm sure it happens. And then horizontal slopes, but really we're interested in kind of these mild and steep situations. Okay.
So in the book's figure for those, in the horizontal slope, it only has a critical depth. Does that mean that the normal slope is 0 or for horizontal?
So for horizontal slope, I guess you don't have a normal depth. Because, okay, so for Manning's equation, the slope in there, if the slope is 0, then you get 0 velocity, right?
Mm-hmm.
So I think what this is saying is, yeah, gosh, I don't know how the horizontal slope plays out, to be honest, because it's just not something that, it's just not often a thing that you encounter in design problems.
Okay.
At least over a long distance.
Right.
So yes, I mean, you're right that like technically there is no normal depth for horizontal slope because due to Manning's equation, if you put 0 in the S term, then you get 0 velocity or 0 discharge, hence 0 depth. So yeah, I think just kind of mathematically there is no normal depth, but because
Okay.
the flow will just deaccelerate and stop and become a pool.
Gotcha.
But you would have to imagine a horizontal slope could be in some continuum between 2 different actual positive slopes. In which case you could achieve a critical depth, but not a normal depth. So briefly, we're going to talk about the computation of gradually varied flow water surface profiles. So WSP water surface profile. And we're going to talk about the standard step method. There's direct step, standard step. There's just two different kind of numerical schemes for solving this. And this is actually, so the standard step is actually what HEC-RAS uses. And what you're doing is you're just balancing the energy equation like you would in a pipe flow problem. But now we're kind of throwing in Manning's equation. And this is how we calculate our head loss. And so the head loss is equal to the average energy using Manning's equation. So you calculate Manning's equation at cross section 1, you go downstream, use Manning's equation to calculate this energy slope. And then you multiply it by the delta X or delta L between the two. So that's going to be our head loss. So the way to do this in HEC-RAS, and we'll talk about that more on Wednesday, is if you have a river, you survey all these cross sections. So these little lines are just topographic cross sections that might look like something like this, right? And then we're basically just solving Manning's equation for one cross section to the next, comparing what the slope of that energy grade line is and calculating our energy loss between the two. Well, this becomes an iterative solution. It's not very straightforward to solve. We will, and you can read about that in the book. Let's see, figure 6.13. I'm not going to show that. The direct step method is not an iterative solution. And the way it works is you can solve that equation that we derived earlier for delta L. And so it says delta L or delta X is equal to stuff, different velocities. So these are the different energy, specific energy terms. So specific energy at 0.2, specific energy at 0.1, and then the difference between the energy slope or the friction slope and the bed slope. So it's actually, if you think about it, this is the direct step method for calculating that water surface profile. It's pretty straightforward. We're just calculating the difference in specific energy and dividing it by the difference in the bed slope and the energy slope. So what I'm going to do is post, we're going to basically just do one problem for this lecture, and it's a spreadsheet. And for the sake of everyone's brain, I'm going to post a little video walking through it for today, and I'm going to have you guys do this calculation in the spreadsheet. And I should add here that this SE bar is if we go to Manning's equation and solve for friction slope, then we calculate that with the 2 points, the two different cross sections that we're analyzing it, and take the average. E needs to be over there, so we're gonna do. Sorry, that's so tiny, but if you solve Manning's equation for slope, for friction slope, you get n squared v squared over k squared, where k is equal to 1 in SI, and k is equal to 1.49 for BG. So that's k squared, and then hydraulic radius, the 4/3. Sorry, that's so tiny, I'll zoom for you. So I'm going to give you a spreadsheet calculation basically where you plug in a delta y. So y1, y2 gives you delta y. And you calculate all these things and it spits out a delta L. And that way you can actually plot that curved water surface profile. So now you guys know how to do gradually varied flow modeling. This is the equation that drives HEC-RAS essentially. And now we're in the real world. We were in kind of playland with uniform flow, and a very important theoretical foundation for what we're doing. But now we can actually calculate flow in natural channels or most any system that we design.
Hey,
You guys have
Joel,
any- Yeah,
on the bottom, for SE, is that k cubed?
that's k squared.
K squared.
Sorry, I wrote it so tiny.
What's the coefficient on the R? I mean, the exponent on the R?
4/3. So you can prove this to yourself. The Manning's equation is V is equal to K over N, R to the 2/3, SE to the 1/2. So if you solve that equation for SE, that's what you get. And sorry I wrote that so tiny. I'll write it bigger. Or I guess it would probably be easier just to write it this way. Okay, I'm just going to share my screen super quick. And we're going to look at the canal that runs through the Grand Valley. There's many canals that run through the Grand Valley. Okay. This is called the Highline Canal. And it siphons water off. Gosh, you got to follow it up way upstream. Okay. Now it's still going, man. Okay. We're going to find it. There we go. So here's the roller dam. That's fairly iconic. It's got those big red towers. And it takes off a bunch of the Colorado River into Back Canyon. And this canal was actually designed, 100 years ago or something. And so in order to design this, they had to use gradually varied flow calculations. They probably didn't actually do that. They had these basic Manning's tables, and they had to use Manning's equation kind of from one point to the next. But nowadays, you would use gradually varied flow because you can imagine you're changing slope, you're changing cross-section area, you're going into a pipe through a tunnel and all these different things. And so they try to keep the slope pretty steady, and maybe you can have the trapezoidal channel shape not change over time, but your slope's going to change. And so we want to make sure that, say we need to divert 500 CFS or something like that, or 1,000, it's probably more, 1,000 CFS from the river, and to distribute it all the way to the end. So this canal kind of runs up against the edge of the desert, and it goes all the way down to Highline Reservoir in Mac. So in order to make sure all that water is able to convey through the channel, they've got to do these gradually varied flow calculations to make sure that they've got enough capacity in the channel that they designed. So just kind of one example of where this is important and plays out. All right, guys, thanks so much for your attention. I'll post this video in the lecture notes, and I can see you for office hours this afternoon. And let me just look at the calendar one more time. So we got the pump design due this evening. We've got homework 9 open channel due tomorrow evening. So make sure you take a look at that either before office hours today if you haven't already. And that's just some basic Manning's equation calculations. I think there's also specific energy in there too. So if you haven't looked at it. All right, I'll see you either this afternoon or tomorrow.
Tell me your office hours.
Today 2 to, let's see,
2 to 3, right?
2 to 3.
Okay.
Good day.
Hey, real quick.
Mhm.
For the project, were you guys getting like a really high system head?
Well,
Sound
the
like-
system
Yeah.
head, what will the system head be when you start it, when you have 0 flow rate?
It would just be the height of the water, like the max height, or the max height.
Yeah.
I don't know why I was getting like 230 plus like 4. I was getting somewhere like in the 600s, and that just seems really, really high. But I'm not sure.
Yeah, that sounds high.
Yeah, I'll go back and check on my work though. For the Manning's equation, you know how it's like H L over D. I mean, for
Darcy-Weisbach.
for Darcy-Weisbach, it's for the length. Do you want us to use like the 300 feet of pipe plus the tank, like the pipe that runs up to the tank?
I think that's
friction
the way
lock.
it works.
That's the way you want it, right?
Let's look, let me just pull up the project description, and then I gotta go in like 3 minutes.
Or it can just wait. It's fine. We can just talk about it.
Okay.
You're good.
Yeah, I would just read whatever I say in the project description.